Welcome to the Rothney Astrophysical Observatory. My name is Jennifer Howes, and I'm very fortunate to be the education specialist for the observatory. We are located 20 minutes outside of Calgary in the foothills of the Rocky Mountains in southern Alberta. I hope you are enjoying your University of Calgary day camp and learning lots about our favorite place, the universe. Unfortunately, you can't come to visit us, so we thought this would be a great opportunity where we could tell you a little bit more about our observatory. We've been here for almost 50 years. We've made a whole bunch of friends and have partnerships with groups such as SOAR, and SOAR actually tests a rocket engine at the observatory site. Here's a crew from SOAR with a test rocket, and very excited to see a launch. And what we're about to see is, wow, this is the rocket in flight. And it's an amazing thing to be able to see. Nothing more exciting than a rocket launch. SOAR is a group of engineering and physics science students who get together and with their love of near-Earth space exploration. And they also are experts in weather balloons. So here you can see them with the 18-foot rocket. This rocket can reach up to 30,000 feet up from the surface of the Earth. Really quite amazing to see. The observatory is home to 5 research telescopes, and I thought it might be fun and interesting for you if I could take you around on a little bit of a tour. Our first stop is the ARCT, one of the largest telescopes in Canada. When we're talking about the size of a telescope, we're talking about the size of the primary mirror, which is 1.8 meters. Let's head over to the big dome, open up the shutter, and have a closer look at this amazing telescope. The size of a telescope is determined by the size of its primary mirror. The ARCT telescope's mirror is 1.8 meters in diameter. The bigger the mirror, the more light that the telescope can collect. The starlight comes in through the shutter, and the light reflects on the large mirror, back up to a smaller mirror, and then down through a series of instruments that collect and interpret that light. The Hercules cluster is 22,000 light years away, and the farthest object that the ARCT has observed was a quasar, and that was 9 billion light years away. Let's head down the hall and check out the Baker-Nunn telescope. This telescope had another life as a patrol camera during the Cold War, and now we use it to look at some amazing things. The Baker-Nunn telescope is another light collector at the RAO. This is an unusual telescope because the telescope collects light with a wide field of view of the sky. The whole sky image shows us how much we can observe at one time. The design is perfect for observing moving objects in the sky like comets or asteroids. This is an image of the Andromeda Galaxy with our old camera, but we got a brand new fancy camera, and isn't this amazing? This is the Andromeda Galaxy, and this is 2.5 million light years away from Earth. This is an all-sky picture to give you an idea of just how much sky we can see at one time with this telescope. This is our new camera, and this just shows you the vast amount of sky that we can observe at one time. And what we're moving towards is a really interesting object. So we're looking at stars and galaxies. And what we're going to be honing in on is something that's called a planetary nebula. And this is the Butterfly Nebula. Let's take a trip up the stairs and go have a look in the dome. The dome is where the telescope is located, and it opens up to the sky. Once again, it's covered by a metal movable dome that is linked to the movement of the telescope. This allows the telescope to follow the stars as they move across the sky from east to west. And I know it might be hard to make out some of these cool details, but what we're seeing right now, this is the bottom of the telescope that we're looking at right now, and it's on a mount that allows you to move the telescope in line with how the stars are moving in the night sky. The telescope is an asteroid hunter, but also using this telescope, astronomer Rob Cardinal discovered 2 new comets. And this gives you an idea of what the telescope looks like and where the light actually enters. So let's move to a different building and check out the Clark Malone telescope. This is the first telescope that was built here on this site back in 1972. And what you can see is when we walk inside here, here's our researcher, Kyle, and he's busy looking up some data that he has observed using this telescope. So let's go inside the dome and check out this really interesting telescope. It's a 0.4 meter mirror that's inside this telescope. And you can see it is on something that's called an equatorial mount. So the top of the telescope is pointing towards the North Star Polaris, and the bottom of the telescope is pointing towards the Earth's equator. And there's the shutter that opens up, and that's what allows the starlight to come in. And the telescope acts like a light bucket. It collects that light, the light moves through the optics of the telescope, and it's interpreted through the instruments that are attached to the telescope. One of the cool features of the Clark Malone telescope is that it can be operated remotely. The astronomer doesn't have to be at the observatory to be able to link up through the internet and to be able to do their observing. There's been amazing things that have been observed with this telescope, including distant galaxies and even a couple of exoplanets. The Triangulum galaxy is 3 million light years away and one of the closest galaxies to our own Milky Way galaxy. The Whirlpool galaxy is 23 million light years away from Earth. That means that the light left that object 23 million years ago before it was collected by our telescopes. You will be learning a ton of cool stuff at your camp about sky science. Here at the observatory, what we know about the objects in the universe comes to us in the form of light. Stars emit light, and that light travels across space. At the observatory, our telescopes collect that light. We research and study the nature of light to understand the information about the star, like how old it is and how far away it is. Kyle is one of our researchers at the observatory, and he operates the Clark Malone telescope. He is an astrophysics student and has been learning about light and optics for the past 5 years. One of the most useful tools he uses to understand, for example, the distance from stars, is an instrument called a spectrometer. He will now share how he observes light from stars.
Hello everybody, my name is Kyle Paltzat and I'm currently the intern at the Rothney Astrophysical Observatory, and I was asked if I could give you a brief explanation on a very cool piece of science that we use to explore space. Now this scientific method is called spectroscopy, and before we get into exactly what that is, I want to take a brief look at the people who really made this science accessible to us today. Now, 2 people that we want to look at is Sir Isaac Newton. And everyone has probably heard the story of the apple falling from the tree and hitting him on the head. And with that, he discovered his theory of gravity. And on top of that, he was a very fascinating optician, which means he liked to look at light and how light reacted with different types of lenses and mirrors. And in his time studying light, he defined this word that we use called spectrum. Now, everyone has probably passed light through a prism, and you see when light goes in one end and out the other, it shows a rainbow. And so the spectrum, in Newton's words, described all the colors of a rainbow. which is very key for what we use, and you'll be hearing that a lot more. The second person is Joseph von Fraunhofer, who actually invented spectroscopy. He created the tools that we use today, and he noticed some very cool things about the spectrum that we use to explore space. And what he discovered is what's called an absorption line. Now, an absorption line, on this next slide you'll see, is little black lines over top of the full spectrum. Now, each of those black lines correspond to a very key blueprint of certain elements. It's like a fingerprint of the elements. And so when light from a star passes through our spectrograph, we get a spectrum in our camera. And then we can look at those black lines to do a lot of really interesting science. Now on this slide, you will see the different blueprints or fingerprints of each element in the periodic table. And we use this because we can just match each of these signatures to our spectrum that we image. It's very, very useful. So there's two types of lines. There's absorption and emission lines. Now these are slightly different. Absorption lines are black, whereas emission lines are very bright. Now each of these correspond to very different types of science and very different types of signatures of what's happening in the star. So we can look at how these lines appear on our spectrums, and then we can tell you exactly what's happening inside that star. Now, when we look at today's spectroscopy, it's very different than what it was back in the day. So I'm going to kind of explain exactly what we do here at the observatory. So on one of our telescopes, we have created a way to get the light that enters our telescope to pass into what we use as a spectrograph. And you can see on here, light enters from one end on the right, passes through a couple mirrors, and then into a prism. And we talked about when light enters a prism and comes out the other end, you get the rainbow. So we pass that light through the prism and into our camera. So we get the rainbow in our camera. And then from there, we can do a lot of interesting science on the computer. So here's our equipment setup. You can see at the top, we have this little white box attached to the telescope, and that brings the light from this red wire into our spectrograph. And then the camera brings the light to our computer. And then from there, we can do our science. And then here's a picture of our actual spectrograph. You can see the red camera on top, and the black box underneath is our spectrograph. So here are a bunch of images from our camera. So you can see at the very top, you get the full spectrum, and then you can see those little black lines through each of the colors. So that's what we're looking at when we want to analyze different types of elements. And our software pretty much reads these images like a book. So you start at the top line, and at the left, it reads it from left to right, and then it goes down to the next line. And it does that till all the lines have been read, and then it puts all that info into what we call a spectrum analysis. And this is what the spectrum analysis looks like. So if there was no black lines, it would be a perfect curve. But each of those really, it looks like noise, but each one of those little lines corresponds to one of those black lines from the previous pictures. And with that, with this final analysis spectrum, we can do a ton of really interesting science. We can look at the composition of the star. So you may have asked, what elements make up our sun? And with this, we can tell you that it's hydrogen and helium. Or we can look at the temperature, because we can look at the elements and we can figure out how fast these elements are being turned into other elements. Or the density, how thick it is, how much of a certain element is in each star. Another really cool thing we can do is we can figure out how fast these stars are moving. And we do this with what's called the Doppler shift. Now, the Doppler shift, you've probably all experienced. So if you've ever been at a train crossing, waiting for a train to pass, and it honks its horn, you'll know that as the train is coming towards you, it'll be a really high frequency. It'll sound higher. And that's because the sound waves are getting condensed as they come towards you. And then after the train passes, the horn sounds lower in a lower frequency, and that's because the sound waves are being extended. So by looking at these lines, we can see if it's a higher frequency or lower frequency, and then we can tell you exactly how fast that star is moving and in which direction. So with all of this, we can do a ton of science, and it makes it really interesting to explore how these stars work, move, spin, and how space works as an environment. So I hope that was helpful, and thank you for listening.
Thanks, Kyle, for sharing with us how we can learn more about stars by understanding the nature of light. The observatory is host to thousands of people who come and have a chance to look through an eyepiece at some of the awesome things in the sky. Fortunately, we're closed right now, but hopefully we'll be open again in the fall. I encourage you to get out this summer after the sun goes down and check out some of the amazing sights in the sky. Check out the summer constellations like the mighty Hercules. Saturn and Jupiter will be visible in the later evening, rising in the east. And also in August, you can take in the Perseid meteor shower. Have fun at your camp and keep looking up at the stars.